This conference will now be recorded.
Okay, hello everybody. I hope everyone can hear me. I wonder if we shall wait a little bit. It's 16 of us now. What you can see on the screen in the meantime is just some fun application on one of the projects that we have done. The one which is this face recognition. It's implemented in JavaScript only. Everything runs in the browser. And then as you can see, I can pick faces from the bottom, and then they will be recognized on the picture that I pick on the top. As you can see, also Hitchcock is recognized on my t-shirt. And then if you have a mask, for example, like these guys here, then it's easy to hide away from the face recognition algorithm. Yes. I guess we have waited long enough. So we just jump in. Welcome everybody to this webinar, which is titled From Lego to Drones. My name is Buzinkay. I'm working for AVINOR. I'm working in DDS, Data-Driven Solutions. We initially picked this name because this covers everything what we do, from data engineering to data science to platform building. Some words about this webinar. So basically, the goal of the webinar is to give you inspirations what can be done with vision and sensor data, and we will demonstrate this through some of our project or cases. This is not a science presentation and not a tech presentation. If we have time after the webinar, I have my colleagues here from the science team, and I'm also doing the data engineering part, so we are open for questions. What it is then? It's a presentation of a journey, what we have done, how in BaseForm we have built up our capabilities around this field. I will also give a very short introduction about some keywords about machine vision and machine learning and so on. So, machine learning. The thing is that most people, someone has to mute at least. So most people talk about machine learning and what's machine learning. For me as a data engineer, the difference between classical programming and machine learning is the one that you can see on the picture. In classical programming, I wrote the program, I gave it some data, and it gave me the answers. In machine learning, I have the data, I have the answers, and I want the machine to learn about the data. So I give it also some kind of algorithm that I pick, and then I want it to spit out rules based on that. The other thing that is nice to know is about pictures, objects. In most of the cases that we have done, I will list it in the next slide. We are dealing with images. So when it comes to images, it's important to know that you have single object or multiple object detection, where we are doing classification that you can see on the first picture. Well, we can tell this is a cat. Then we also do classification and localization. We can say this is a cat and here is the cat. You can see the cat in the red rectangle. The next thing is when we are doing multiple objects, it's an object detection. And there we can say, oh, this is a cat, this is a dog, this is a small duck. We are locating the objects in the picture. You can see it in the rectangle. And then we have the most advanced, well, a very different one, where we do instance segmentation. So where we are clearly defining the boundaries of the object that we are detecting. You can see both the cats, the dog, and the duck are clearly identified. These detections usually based on a machine learning model or an inference of a model. Inference means that we are executing our model over a given data set and we get the results. The thing is that in certain projects, when we don't have enough data, we are not using machine learning, but we are just using something called computer vision or machine vision. An example for that would be a technique that is called background subtraction. We are using KNN. What you can see on the right is not playing in this PowerPoint, but it's a video of a car and a person passing by and cars in the background. Those are moving objects. So a video is basically a frame with several frames in a stream. And then what we are doing is that we are looking for the difference between the frames, and based on that we can subtract the moving objects. That's what you can see in black and white on the middle and the right side. To be honest, this is the technique that we have been using now in certain factory conditions where we haven't had enough data to train up a machine learning model. We just went for machine vision or computer vision. Okay, so after this introduction, let's jump in and let's talk about a little bit of projects. BF is the meaning of base form. The first project that I had as a base form, I'm a data engineer, that's very important to say. So everything that we are presenting is viewed through my eyes, through a data engineer's eye. The first project that we had was UCAIR. It's a drone company that's inspecting solar farms. We've used TensorFlow and TensorFlow.js. I should present that case. The next one was a hobby project for me where I bought a Coral dev board, which is very similar to a Raspberry Pi, but it's from Google and it has a special chip to speed up model evaluation. I did a Lego detection project using this. The next one is a baseform project where we had a proof of concept for AVINOR. I will also present this case. It's done in TensorFlow. We have two factory projects running as of today. It's very unfortunate that they are under NDA, so I cannot talk about the very details of the machine vision part that we are doing, but I will share some interesting information, what they are, what we are doing, what pipeline we have built there. The first factory case, we have proven that we can do machine vision and machine learning detection based on sensor data. The customer was very happy, so they ordered the second phase and we are scaling up the whole pipeline there. The second factory case is in an upstart phase. What you can see on the picture is just a small toy that I built in JavaScript to play with machine vision in JavaScript. You can see a Lego block and you can see on the black and white picture that it's detecting the red color. Okay, let's jump in and let's see our first case, which will be the Lego detection. So for me, this was a data engineering project. I really wanted to play with the Google Coral dev board, as I mentioned. It was to catch the bad guys. As you can see, there is a clear picture of a Lego figure, which is Luke Skywalker. And what I have done is that I've taken a Google pre-trained model and I did transfer learning. The meaning of transfer learning is that I can retrain the model from Google from scratch, or that's the full model retraining, or the last layer only. In this case, I have done both, and I've done the full model retraining. It's not that many images that I use for training, approximately 800, and you can see the result on the right. So there are the people we are looking for. The policeman is not a wanted person, so he is not in a red rectangle, but the others are. This demo I very often present in conferences to show that we are aware of how machine learning based image recognition is working. So the next case, or this was my real first case in data engineering, data science, was a company called UCAIR. They've been bought up now by another company from England. They are a customer in Germany. They have done a drone inspection of solar panel farms. What you can see on the right, those are pictures from infrared cameras that they are carrying on the drones. Based on these infrared pictures, they are capable of detecting more than 40 failure types on your solar panel. I think it's 60, and they have some subcategories and so on. So when you are inspecting your solar farm, they will tell you that, hey, this panel is underperforming, or this one has an error. Let's talk about the challenge that they have. So the challenge is that the picture that you can see here is from a high altitude. So the drone went up very high and it recorded the whole farm. On the other hand, this is not allowed in most European countries, or you need a special permission to fly over a given height and have this picture. This picture they can use to create a map of the solar farm. But in most cases, they haven't had that, they only had the pictures. There are different techniques that you can create a map of your drone pictures if you put out objects before the flight, but they never done that. So the challenge that we've been facing is rebuild the structure of the solar farm based on the images that they have. So what you have to know about the solar farm inspections, that each drone flight is resulting approximately 1,000 images, black and white. They have embedded GPS information in the flight. Sometimes they have infrared pictures, and some farms are not even on the satellite pictures because they are so newly built. So what I have done in terms of data engineering, I gathered all the data from the pictures. Each picture had a GPS tag. We reconstructed the flight path. That's the one that you can see with red on the picture. And I reconstructed where the picture was taken. That's what you can see with the green circles. Then we have trained up a machine learning model to recognize the solar panels. That's what you can see on the right. So the drone picture is the grayscale picture. And the picture under that, where you have with this lime green color, the recognition of the solar panel. As you can see, it's not detecting those objects that are laying between the panels as a panel. So this was the first step towards to be able to reconstruct the structure of the farm. In the next step, we actually went further and we retrained the model, and then it was able to detect each panel separately, not only the huge panels, but that was not part of our project delivery. We just gave ideas to the customer with this. So here the data was for the images. We put them on AVS for machine learning, and the data for this visualization is on GCP, Google Cloud. I would say this is a pretty static thing, not that many moving parts. But this was our first case. This is where we got to know with position-based image recognition. And then what happened is that AVINOR, which is the Norwegian company that is owning and responsible for the management of Norwegian airports, has seen our solar panel demonstration and the LAGO demonstration, and they had an idea that they wanted to test with us. The idea was that as of today, they have huge airports, and the yellow line that you can see on the picture is where the fence goes around the airport. As of today, it's a human resource that is going around the fence every day or every second day and inspecting it manually. So obviously, AVINOR would save a lot of money if this could have been automated. So what has happened here is that we partnered up with a company called SenseLoop. SenseLoop is the only company in Norway that has all the flight permissions in Norway to fly in special conditions. And they're also very good in carrying objects with their drones. So they have different LiDAR sensors, laser sensors, and they have also different cameras that they can install on their drones. So we got this SVOLVÄR airport project. And what you can see here is that we were collecting different data sets from the drones. We had pictures, full frame 4K pictures. We had video, 4K video. The challenge with the 4K video is that it was not GPS tagged. There is some military option for that we haven't evaluated. We had the Regal Minivux is a laser on the drone. It's not a high resolution drone, so we haven't used those pictures that much. And then we had a laser on the ground. It's a pretty heavy laser, the Regal VZ400i. So it has to be installed in a car or on a helicopter, and that it makes it impossible to carry on a drone, and there are costs related to that. But it's very nice for us to collect ground information or basic information about the fences and the airports. And then we also had some thermo data. I will show you how is that looking, but on the thermo data, really the fence objects are not visible. What have we done here? So we get the drone pictures uploaded to Google Cloud. There is an option. So what makes SenseLoop very special is that they have a permission to fly drones remotely through 5G network. So they can sit in Oslo and fly a drone that is up north. And then the drones also have a small box, which is a kind of a hangar. They can also pre-program flight routes. So they can send out the drones from the hangar. They can come back with the drone to this hangar, and they can download the data from the drone. That thing was not part of our project, but we also investigated a little bit what are the options there. So we manually uploaded the data to our cloud-based platform. This was our second big data project for Vision. So what we have done is that we extracted the metadata like we did for the solar panel project. We also went through all the data and we manually linked it, and we reviewed the data as you can see it in point 3. We annotated which is good data and which is bad data. Here we have done it manually. Later on now we are doing it automatically. After we reviewed all the data sources, we have focused on the full format images and on the high resolution LiDAR data. And to present this was a proof of concept for the customer. So we have developed an internal web-based tool for visualizing the data and the results in the context. If we have time, I can show you that one. So a little bit about the analysis. The pictures are coming, it will be much more visible there. What we have done is that on the pictures, we have trained up a deep neural network, deep lab model based on TensorFlow to recognize the pixels in the image belonging to a fence. So if you remember at the beginning, I was talking about segmentation. So we segmented out the fence. We also done some segmentation of people and cars using existing models from Facebook and Google, just to prove to the customer that it's possible to segment out these things. Once we have detected the fence in the picture, we also detected the mesh or the body of the fence wire in the picture. This proven to be the most difficult part of the analysis. It was very sensitive to lights and material of the fence. We used a very simple method of static color ranges for the two types of fences, metal and some plastic. We also tested other techniques, but those proven not to be so effective. We figured out that it has to be a very pragmatic we have to be very pragmatic, so it's much better to discuss it with the drone operator from what angle they are filming and taking the pictures. We also did analysis of the integrity of the netting of the fence wire. We used different machine vision techniques, and we used some Gabor filter for hole detection, and that will also be shown in the pictures. So now the pictures. So what you can see on picture A is the high resolution image from the camera on the drone. The picture that you can see on picture B is the video image. You can see it's not that crystal clear. What you can see on C, or well, eventually you cannot see it unless you zoom in very much, is the low resolution LiDAR laser scanning data. That LiDAR was installed on the drone. What you can see on picture D is the high resolution LiDAR scanning that was done from the ground on a stationary LiDAR. What I have to say about this laser scanning, it's millimeter precision, and it results a really high data density and high amount of data. The data amount was 22 gigabytes and 900 million data points for the scanning of this airport. We were planning to use this as source of truth, so we can compare the LiDAR data to the findings that we have on the pictures. We also created an algorithm to be able to cut up the huge data to smaller chunks, as you can see on picture D, which is only showing the fence between two poles. This is to speed up the comparison between the picture and the LiDAR data. And you can also see on picture E is the infrared vision on the fence, where you really can't see the fence. So we were pretty quickly eliminated that as an option. The next one, you should really get very close to the picture, and I will go back later on to this picture, but I show you. So this is the picture that we get in high resolution from the drone, and then this is the model that we train. And this is the model that we trained up for the segmentation. So this is that was segmenting out for us the fence. And then here is our black and white representation of the fence, where hopefully you can already see that in the middle there is a hole in the fence. The next one is really where we are detecting the hole in the fence in the middle. I hope it's visible, the black hole in the middle of the fence. So if I go back now to the first picture, you can see in the middle of the fence that there is a hole, and that is not really visible for a human eye. We had the same findings that when we started this project with our droning partner. They have installed the fence in the backyard, and they took some drone pictures with that one, and they also created holes on the fence. They created 3 holes, one bigger where a person could go through and 2 smaller. When we looked at the pictures, we could clearly see the bigger hole where a person could go through, but we didn't recognize the smaller ones until we also have done the same color ranging that you can see here, where it was obvious where there are the holes on the fence. Yes. This is just a dataset example about the high resolution LiDAR data. So also the challenges here, as you can see that there are certain objects in front of the fence, like trees or buildings and so on. So we also suggested to the customer that not everywhere we can do machine vision based recognition of the fence. This is the LiDAR data or the infrared data where we proven to the customer that we can detect people that you can see on the left. We can detect if a car has arrived to a parking spot, for example, or we can see it on the bus that the bus's engine is hot and the brake of the bus is hot and that there is a driver in the bus. These can be combined with the normal machine vision that we have done. Here are the samples for the other type of object detection where we did segmentation for cars or people. This is just to prove that this can be done with any algorithm from bigger companies like Facebook or Google or open source projects. Yes, so this was our AVINOR project. The customer was pretty happy with our findings. We have delivered this report. And then we have summarized at the end of the report that the technology is not ready yet. The high resolution LiDAR drones are too heavy to carry on around the airports, and then also the recognition of the fence is from the drones through camera is very sensitive to light conditions. And you can imagine that up in Norway, up in the north, as you can see on this picture on the bottom, the weather can change drastically. And when it's snow, when it's rain and so on, it's very difficult. But the customer was very happy and it gave them a lot of inspiration. So they have started a dialogue with the internal GIS team, the internal mapping team, what they could have done more with use of drones. Yes, so our current cases, it's a factory case with sensors. As I said, this case is under NDA, so I cannot really say what is the customer doing in the factory and who is the customer. But this is where we started our real industrial journey. So the customer has several production lines where they are having heavy machinery. We placed out 2 cameras to monitor the production on the line. We also placed out vibration and sound sensors. And we also integrated our pipeline with PLS data. So we are aware if the machine is stopped or the line is running or it's stopped. And we also have a LabVIEW based system that we can present to the customer showing the status of our recognition, and they can also tune the parameters of our recognition system. We started with several lines, but we've been focusing on one line where we have spent a lot of time of fine-tuning the position and placement of the cameras and lighting for the cameras, because the cameras are also tracking colors in that case. So we found that the cameras in the industrial environment are very sensitive to light conditions. And this is a real pipeline. So what's happening here is, I can probably go to the, so the use case here is that if the camera is detecting something not okay in the pipeline of the customer, we can send a status message and the alarm to the LabVIEW. So here is our machine-based algorithm, machine vision-based algorithm is running on the camera data, and we have a machine learning based vibration and sound detection running, and both can warn the customer about problems on the line. So what we have done here is that we have placed out these sensors. As you can see, the camera, the microphone, the vibration sensor in the factory. We also placed a button there so that the customer can punch the button when they think there is an error on the line. So we can tag all the incoming data for later inspection. And also the data that is produced when they are punching the button is also high resolution data. What's happening here is that here we automated everything. So from the factory, the data is automatically copied into Google Cloud, where we can do data science experiments and where we can do development. So we can, for example, when we train the machine vision models that we use for detection, we downloaded the pictures, we created a video from it, and we could just analyze that, and we could build our algorithms on that. When we were finished with the algorithm, we downloaded that into the factory to a special Raspberry Pi that was responsible for the analytics of the picture stream. And then when the algorithm has detected that there was some error on the line, we just signaled the red light for the customer. This project, we completed phase 1, where we had several use cases for several lines. We both proved that it's possible to detect errors on the line with camera and vibration. With vibration, we can also do some limited prediction. So we can tell in advance that there will be some problem on the rotating machinery. The customer was pretty happy with this case. So when we completed phase 1 and it's approved, now we are phase 2, where they would like to upscale the whole line, upscale the whole project, and make it more robust for industrial use. And they would like to use it on more of the industrial lines. They will also, we also in a dialogue with another industrial customer, where we will do the same thing, where most likely we won't do GCP, but we will use Azure, but we will deliver the same factory data science and development project. And there is some slide here where you can see the vibration data events. So each horizontal line, you can see there's a timestamp, and then you can see the frequency spectrum on the x-axis. So basically a horizontal line where you can see the red circles. We circled that the data that we were getting from the vibration sensor was out of the range that we allowed or that we wanted to monitor. And the next picture, what you can see here is basically those are the pikes on the horizontal line of the previous chart. So if I go back here, let's say if you pick 1255 and you imagine a horizontal line through the whole graph, and you can also see that outside the red circles we have some colors. So that is these spikes, and these spikes are showing to us that there is some problem, there is some vibration created issue on the line. Yes, I think we are over the half an hour now that we were planning for this presentation. I don't know, this is my first webinar, so I guess we are open for questions if there is any from anyone. And in the background now, you can see some of the fun stuff that we have done. Yes, thank you for your patience. Any questions?